morning, children. Welcome back to your chemistry class. So, in this chapter of chemical bonding and molecular structure, in the previous video, we were studying about the electronic concept of your chemical bonding, in which we were doing the ionic or the electrovalent bonding. In that particular video, we came across a new word, that is lattice energy or lattice enthalpy. So, today I will further describe you what is lattice energy, what is lattice enthalpy, and move over to how the lattice energy is calculated, okay, by the Born-Haber cycle. So firstly, let us understand what is lattice energy, right? So cations and anions, they attract each other by the electrostatic forces of attraction, and they form a molecule. What kind of a molecule it is formed? A plus B minus. Now, since the electrostatic field of a charged particle, it extends in all the directions. If you look at the figure, you will see that a positive ion, it is surrounded by number of negatively charged ions, while the negatively charged ions, they are similarly surrounded by number of positive ions. Right? So these cations and anions, which are arranged in a systematic manner in an alternating cation anion pattern, right? This kind of a crystal, it is called as what? Crystal lattice. And the process of clustering these ions, it always increases the force of attraction, and thus potential energy, it decreases. I repeat, this is what I had also explained you in the previous video. What did I say? That during the process of clustering of these iron, when it increases, what happens? The force of attraction also increases, and therefore the potential energy decreases, right? Thus, the energy released when the number of positive and the negative ions, they are condensed into a crystal to form 1 mole of compound, that is called as lattice energy. Therefore, higher the lattice energy, greater will be the ease of forming the ionic compound. I hope this is clear. This was also explained to you in your previous video. What did I tell you? That if lattice energy is greater, then ionic compounds are formed. So, if the energy that is released is always greater than the energy which is used, right, then it is always the formation of ionic compound, right? Thus the formation of ionic compound, you can always remember like lattice energy plus your electron affinity, it should always ionization energy. I think this I had also explained you in your previous video. Right, now we come to what is lattice enthalpy. Lattice enthalpy. In lattice enthalpy, we are going to talk about two definitions. What are those two definitions? It is lattice dissociation enthalpy and lattice formation enthalpy. So firstly, let us understand these 2 points, or lattice enthalpy, then I shall explain you Born-Haber's cycle. So first let us talk what is lattice dissociation enthalpy. The enthalpy change when 1 mole of an ionic lattice, it dissociates into isolated gaseous ions, it is called as lattice dissociation enthalpy. What did I say? Let me write it down for you. Lattice dissociation enthalpy. So how can we define this? The enthalpy change when 1 mole of an ionic compound or ionic lattice dissociates into isolated gaseous ions is called what? Lattice dissociation enthalpy. Clear? For example, if you want to understand Na plus Cl minus, right? This is in the solid state. It dissociates, the ionic lattice, it dissociates into what? Isolated gaseous ions. That is Na plus, which is in the gaseous state, plus chlorine minus, which is also in its gaseous state, right? And the net heat will be equal to 788 kilojoules per mole. So what is this? This is your lattice dissociation enthalpy. How do we show lattice dissociation enthalpy? It can be shown by delta LH. What is this called as? This is called as your lattice dissociation enthalpy. Clear? This value what I have written over here, it varies from book to book, right? So you do not have to restrict to what the value I have given you. It can be 787.5 or 788. It depends on the different books, right? Then what does this statement make us understand? It says that the lattice enthalpy tells us how 1 mole of this ionic lattice NaCl, right, which has, what is the molecular mass of this? 58.5 grams of sodium chloride, okay? It dissociates into gaseous sodium and gaseous chlorine ions, and hence it supplies how much heat? 788 kilojoules per mole of the energy is given out. So from the value of this lattice enthalpy, it can be concluded that an ionic compound is more stable if its lattice enthalpy is large, right? So few important points, again I am repeating if you have forgotten, that an ionic compound is said to be more stable when the lattice enthalpy is large. Then an ionic compound has large value of lattice enthalpy when the charge densities of its ions, they are also large, because they attract each other then more strongly, okay? Then smaller ions, they have greater attraction for each other because of their higher charge density. Therefore, the ionic solids of smaller ions, they have larger values of lattice enthalpy. I hope this is very clear to all of you. Now we are going to talk about the second one, that is the lattice formation enthalpy. So this was the first one. Let me talk about the second one, that is your lattice formation enthalpy. Now always remember your lattice dissociation enthalpy, it is also represented by delta LH or it is also represented by the alphabet U. Okay, in some books it is given as U, in some books it is like delta LH. Now talking about lattice formation enthalpy. How can we define what is lattice formation enthalpy? The enthalpy change when 1 mole of an ionic lattice is formed from its isolated gaseous ions. That is called as lattice formation enthalpy. So I write it down over here. The enthalpy change when 1 mole of an ionic lattice is formed from its isolated gaseous ions is called lattice formation enthalpy, right? So example, let me write down in terms of NaCl only, that is Na, which is in its gaseous state. When combines with the chlorine ion, which is also in its gaseous state, what it is going to form? It is going to form 1 mole of your NaCl ionic lattice, right? Where your delta H will be equal to minus 788 kilojoules per mole. Fine. So how do we denote lattice formation enthalpy? We denote lattice formation enthalpy by delta Hc. Okay. So this is how we show the lattice formation enthalpy. And remember, lattice dissociation enthalpy is just opposite to lattice formation enthalpy. And therefore, we can say that delta LH, what is this? What have I shown you this as? Lattice dissociation and enthalpy is always equal to minus delta Hc. What is delta Hc? That is the lattice formation enthalpy. Is that clear? They are just opposite. So your lattice dissociation enthalpy is always equal to minus lattice formation enthalpy. That is, the value of your lattice formation enthalpy is always negative, and thus we can say the process is highly exothermic. Is this point clear? Because this value, that is your lattice formation enthalpy, is in negative, therefore the reaction will always be what? Exothermic in nature. And why it is exothermic? Because due to the strong electrostatic attraction between the ions of the opposite charges. Clear? Therefore, large amount of energy is released as the ionic bond is formed. I hope till here everything is clear. Now we are going to understand how to do the calculation of the lattice enthalpy. So when I say lattice enthalpy, we are going to understand how to find out the value of lattice dissociation enthalpy or lattice formation enthalpy. And you know, once you find out lattice dissociation enthalpy, you can easily find out lattice formation enthalpy, or if you find out lattice formation enthalpy, you can easily also calculate your lattice dissociation enthalpy, right? So coming to Born-Haber cycle. Now, thermodynamic properties, like for example your enthalpy of sublimation, your enthalpy of atomization, then ionization enthalpy, your electron affinity, your enthalpy of formation, all these enthalpies or thermodynamic properties, they are used to calculate the lattice enthalpy. Clear? So the method that is used to calculate this lattice enthalpy is done by Born-Haber cycle, right? So to calculate the lattice energy of the ionic solids using various thermodynamic values, it is called as Born-Haber cycle. And in this method, it is assumed that whether a substance is formed in a single step or in several steps, the standard enthalpy of formation will always be same. I hope that's very clear. So once again, what is lattice energy that we had discussed? The lattice energy, which is termed as U of an ionic compound, it is defined as what? The amount of energy that is released when 1 mole of the compound or ionic lattice is formed by the combination of the constituent gaseous cations and gaseous anions, right? So, and it's always given in what sign? It is always given in a negative sign, and therefore it shows an exothermic reaction. Why? Because of strong electrostatic forces of attraction which binds the ions to form a strong ionic bond. Clear? So now we are going to move ahead how to understand to find the lattice enthalpy by the Born-Haber's cycle. So here firstly I am going to give you a formula and also going to explain it to you. So over here the formula for Born-Haber cycle is delta F, this is equal to plus half delta D plus ionization energy or ionization enthalpy plus delta EgH plus delta Hc. Now let us understand what all these thermodynamic properties that are involved in your Born-Haber cycle they mean. Okay, so your delta FH, what is this? This is your enthalpy of formation, right? This is the standard enthalpy of formation, right? Then what do we have? We have delta SUBH. What does this mean? It means enthalpy of sublimation. Okay, SUB, sublimation. Then we have what? Delta DH. Delta DH. What is this? Delta DH means enthalpy of dissociation, okay, of the gas. Then we have done this. Then IE, what is this? This is your ionization enthalpy. Then we have delta EGH. Okay, so what is this? This is your electron gain enthalpy. And lastly we have delta HC. What is delta HC? This is your lattice formation enthalpy. So if you remember all these thermodynamic properties, then it will be very easy for you to calculate the lattice enthalpy. Clear? And this is the formula that you have to remember. Now remember, there are how many? 6 quantities. 1, 2, 3, 4, 5, 6. So out of these 6 quantities, if 5 quantities are given to you, you can automatically calculate the 6th quantity. Is that clear? So now I am going to explain you the Born-Haber cycle with the help of one example. So the first question says, construct a Born-Haber cycle for NaCl and calculate the lattice enthalpy, and in the question it is given that your enthalpy of sublimation, okay, of sodium, it is equal to enthalpy of sublimation. No, this is how we write. This is equal to 109 kilojoules per mole. Okay. Then also in the question it is given to you enthalpy of dissociation, and enthalpy of dissociation of chlorine is given. How do we write? DH. So the value of this is 244 kilojoules per mole. Then also your ionization enthalpy of sodium is given to you as what we write, i.e. the value of which is equal to 496 kilojoules per mole. Then electron gain enthalpy is also given, which is written as, of chlorine is also given, which is written as EGH. So the value of this is minus 350 kilojoules per mole, right? And even the standard enthalpy of formation, which is also represented by delta FH, okay, of NaCl is given to you, which is equal to say minus 411 kilojoules per mole. Right, now you have to construct a Born-Haber cycle. So firstly I will teach you how to do the calculation based on this formula, and also I am going to construct a Born-Haber cycle just now. Firstly, let us understand how to calculate the lattice enthalpy. So over here, let's write down this formula, that is the standard enthalpy formation, delta FH. This is equal to the enthalpy of sublimation, delta F, plus half of your enthalpy of dissociation, DH, right, plus your ionization enthalpy, plus the enthalpy of electron gain, plus electron gain enthalpy, that is this, plus lattice formation enthalpy, that is delta HC. So now we know the enthalpy, standard enthalpy of formation, we know enthalpy of sublimation, we know enthalpy of dissociation, we know enthalpy ionization enthalpy of sodium, we know the electron gain enthalpy. We need to calculate lattice formation enthalpy, right? So your lattice formation enthalpy will be equal to what? The standard enthalpy formation minus the enthalpy of sublimation plus enthalpy of dissociation plus your ionization enthalpy plus your electron gain enthalpy. Clear? So this is equal to what? Minus 411 minus what all is given inside? This is how much? sublimation is 109 plus half of enthalpy of dissociation is given to you how much? 244 of your 244 plus ionization enthalpy of sodium is 496 minus electron gain enthalpy minus 350. Okay, so all this comes out to how much? As minus 788 kilojoules per mole. So what did we get? Lattice formation enthalpy is how much? Your lattice formation enthalpy has come out to be minus 788 kilojoules per mole. This is what I had told you, that the lattice lattice formation enthalpy is always negative. That is your minus 788. Okay. Now if you have to find out the lattice enthalpy of sodium chloride, so your lattice enthalpy of sodium chloride, that is, what are we talking about? We are talking about lattice dissociation enthalpy, right? Or U, what we are talking, that should be positive. So this will be equal to 788 kilojoules per mole. I hope you have understood how to do the calculation. Now I will also show you how to show the construction of your Born-Haber cycle with respect to NaCl. So where should I show you? So let's see this. Sodium, which is in a solid state, combines with half of chlorine, which is also in the gaseous state, to form NaCl. So here what are we going to observe? The standard enthalpy of formation, which is also written as U. Clear? I hope this is very clear to you. Now, what did we understand? This the formation of the compound can be in one straight form, or it can be in other way also. How? Let's see that. I'm constructing the Born-Haber cycle. So this sodium which is in a solid state will change to sodium in its gaseous state. How? By your enthalpy of sublimation. Enthalpy of your sublimation, right? And from the gaseous state it will convert to the gaseous ion. So what are we going to see here? Here we are going to see the standard enthalpy formation, which is also equal to your ionization enthalpy of the sodium gas. Okay. Then let's look at this chlorine. Chlorine, it's going to convert to chlorine gas first. So here we are going to see the half enthalpy of dissociation. Okay. Then this gas converts to what? Chlorine ion. Chlorine ion, which is in its gaseous state. So here you will see electron gain enthalpy, that is Eg, right? And these two ions, they will combine, and they are going to give you NaCl, where we are going to observe the lattice formation enthalpy. Lattice formation enthalpy, how do we write? Like this. So this is how we have to show or construct the Born-Haber cycle. That is, the solid, it will start subliming first to the gaseous form, and then by ionization enthalpy it is going to convert into its ionic state in the gaseous form. Then this chlorine gas, by the enthalpy of dissociation, will first convert to chlorine gas, and then by electron gain enthalpy it will convert to the negative chlorine ion, which is also in the gaseous state, and they then combine to form through lattice formation enthalpy they form NaCl, or straight away Na plus Cl, half of Cl2 with your lattice energy can combine to form NaCl. So this is how we construct a Born-Haber cycle. I hope you have understood this. Now today I am going to give you 2 more questions on Born-Haber cycle for practice, and then I shall start with your covalent bonding in the next video. Okay, so note down the question. To construct a Born-Haber cycle for lithium fluoride LiF and calculate the lattice enthalpy, right? It is given that the enthalpy of sublimation of lithium, which is equal to 155.2 kilojoules per mole, right? Then your enthalpy of dissociation of your fluorine will be equal to 150.6 kilojoules per mole. Then your ionization enthalpy of lithium, okay, this is equal to 520 kilojoules per mole. Then your electron gain enthalpy of fluorine, this is equal to minus 333 kilojoules per mole. You have under the standard enthalpy of formation of lithium fluoride, it is equal to minus 594.1 kilojoules per mole, right? So you have to calculate the lattice enthalpy as well as show the construction also of the Born-Haber cycle of lithium fluoride. Okay, and one more question you take, construct Born-Haber cycle for calcium chloride, and you have to calculate the lattice enthalpy, right? And it is given that the enthalpy of sublimation of calcium. So construct Born-Haber cycle for calcium chloride and calculate the lattice enthalpy, and it is given that enthalpy of sublimation of your calcium, it is equal to 121 kilojoules per mole. Then the enthalpy of dissociation of chlorine, it is equal to 242.8 kilojoules per mole. Then ionization enthalpy of calcium, right, this is equal to 2422 kilojoules per mole, right? And your electron gain enthalpy of your chlorine, it is minus 355 kilojoules per mole, and the standard enthalpy formation of calcium chloride is minus 795 kilojoules per mole. So these two are the questions for you to do. Okay, so only till here. Now the next video I shall begin with the covalent bonding. Thank you.